Now starting the next set of rapid fire for the 2025 10A. We're on problem 6. I have my time written down at this point, by the way, as like 17 minutes is when I was kind of around this point. So I had a lot of trouble with coming up with my strategies on the two previous problems, 4 and 5. So I say that only that those of you who also had trouble, you feel okay, it was a weird problem. Are there some people who got it really quick? Yes. My score on this, I haven't calculated it yet, but it was like 18 right and 7 skips, which is much lower than I did last year for most of them, anyway, for B at least. So again, I think that the test cutoff is going to be similar to the 2024 10A. That's what I think. So if you're above 93, you got a good shot, and maybe even below that it might dip, just because of how much time some of them took to develop their thought processes. In an equilateral triangle, each interior angle is trisected by a pair of rays. The intersection of the interiors of the middle 20-degree angle at each vertex is the interior of a convex hexagon. Doesn't say it's regular. What is the degree measure of the smallest angle of this hexagon? So I'm going to go here and just try to draw fairly accurately an equilateral triangle. And then, actually, I don't even really like that. We're going to do it again. No, we're not editing. Let me just do it over here so it's straight on. That looks a little bit better to me. Okay. Then if I trisect this angle, like that, and I trisect this angle like that, keep in mind, what do we know as of right now? We know this angle here is 20. You know that this altogether is 60. So you know that this angle right here is 100. Okay, then keep those in mind. We might want to do that elsewhere as well. So now we're going to draw this one. Something like this. If I look inside, I've got 1, 2, 3, 4, 5, 6. Okay, so now we've got to figure out, man, that's just not big enough. It's too crowded. Sorry, we're going to have to do it one more time because the marker's a lot bigger than my pen. So we're going to go like this and like this. Maybe I will edit, but probably not. I'm just not going to have time. Okay, and then that'll give us more space. There's just not enough space in there to really draw accurately. You're not going to have a perfect drawing, by the way, so you just kind of have to accept it. You have a straight edge, probably use it. I don't have one for my marker. Okay, so now that's a lot better. So this angle here was 100. This is 20 there. This is 20 here. This will be 100 here. We're trying to work our way inside. So if we have 60 up here and we have 20 here, this is also 100 here. Let's see, what else do we know? Okay, so this will be 100 over here as well. And this angle in the middle is 20. And this angle here is 20. But this angle right here is the exterior angle of this bottom triangle. So that makes it 120. And so this being 20, this is going to be the same thing. This angle here is 20, makes the sum of the two remote exterior equal to this, or interior equal to this exterior. So now let's add 240 and 20 to get 260. The quadrilateral is 360, which makes this angle right here 100, and this angle right here will also be 100. So we found that one. The other one that you're going to get here is when this is 20 and 20, you're going to have a triangle that meets right here. So I've got 20 and 20, therefore it's also isosceles, by the way. That means this angle is 140 and that angle's 140. If you continue to inspect going around, you're going to see that it alternates 140, 140, 140, and then 100 and 100 here. Mine's not drawn to scale. You're going to have to conceptualize unless you're really good with your straight edge and you like got a compass out and stuff and made it look all perfect. Otherwise, you're going to have to conceptualize what's happening here. Just to double check, if I add 3 times 140 plus 100, I'll get 240 times 3, which is 720, which is the sum of the interior angles of a hexagon as an additional check. That formula, by the way, is n minus 2 times 180. Put a 6, you're going to get this. So the answer is going to be 100, which is C. Let's get on to the next problem. This problem is where if you do know how polynomial division works and you know the factor theorem and the remainder theorem, you can pick up some time on this problem that you might have spent on that mountain problem. Like I spent a long time on that. I don't even know how long it was, but it must have been a while. But this one did not take me long at all. I hope that all of you, when you got here, felt comfortable. If you've done long division and you know the factor theorem and the remainder theorem, these are typically covered second semester of Algebra 2. If they're covered there, they're definitely covered in pre-cal. So you can learn them in both of those places if you have a textbook. Suppose A and B are real numbers, not necessarily integers. When the polynomial x cubed plus x squared plus ax plus b is divided by x minus 1, the remainder is 4. Here's what the remainder theorem says. It says if you take a polynomial and you divide it by x minus c, so if you do this, then the remainder, this is a small notebook concept, so write it down, the remainder is equal to p of c. This is why you can just plug in 1 to here, and it must be equal to the remainder of 4. If you knew this, it pretty much trivializes the problem, and even if you didn't, you could do long division and create the same thing. But what you'll do is you're going to plug in 1 up there, you're going to get 1 plus a plus b, and this is going to need to equal 4, which means that a plus b is going to equal 2. That's what this means. As an example of that, let's make up a polynomial really quickly just to teach you the concept. We'll just make up something. This is not what they are, but let's say it's plus x plus 3. Okay, I'm making this up. It's not that problem, just similar. And I'm going to divide this by x minus 1. You can go ahead and do synthetic division, which if you've learned, you're just going to go like this. And you're going to drop this one down and multiply, and you add going down. There's nothing to add here, so you just put 1, add 1 and 1 to get 2. You multiply here with that number, and you put it here. You add to get 3, multiply to get 3. So weird. It actually, it came out to the other remainder. Never mind. So yeah, this is your remainder, and this is your reduced polynomial. So you would have x cubed plus x squared plus x plus 3 divided by x minus 1. This part makes your quotient. So it's x squared, 1 less power than this, plus 2x plus 3. So x squared plus 2x plus 3. Again, this does not have to do with our problem. I'm demonstrating the concept here so that you understand why it works. And then it's plus your remainder of 6 over x minus 1. That's known as the division algorithm. You also need to know that. But look what happens if I plug 1 into this expression. 1, 2, 3, 6, which is exactly what our remainder was when we did the synthetic division over here. The first part is your quotient coefficients. The last number is always your remainder, which is why if it's going to hit the x-axis there, like be a root, your remainder would have been 0 because you want p of c to be 0, making c a root of the equation. So back to our problem at hand. For some of you who don't know that, I didn't want you to be lost about why this works, so I thought I would give you a quick explainer on why that's justified. Okay, continuing though, when the polynomial is divided by x minus 2, again, you're subtracting c, so c is actually 2. We're just going to plug 2 in. 8 plus 4 is 12. We're going to get 12 plus 2a plus b is going to need to equal 6. They ask, what is b minus a? I'm just going to go ahead and subtract 12 and get that 2a plus b equals negative 6. And then I'm going to split this into a plus 2 equals negative 6. Because this is really how did I do that? That's a plus b. And I'm just visualizing the a plus b becoming a 2. We'll now subtract 2 to get a is negative 8, and we'll drop negative 8 right here. Just put negative 8. What do I have to add b for? B is going to be 10. So negative 8 plus 10 does equal 2. All right, so now we want b minus a. So what is 10 minus a negative 8? They didn't put 2 here, luckily for those of you who might have put 2 on accident, but it is going to be E18, 10 minus negative 8. On to the next one. Again, if you like logical reasoning problems, which is all this one is, you can pick up some speed on this problem as well. A lot of you might have gotten paralyzed and not sure how to begin. How you begin is just with assumptions. You just make an assumption and you test it out. Let's see what that looks like. Agnes writes, this is problem 8 for the 10A, 12A, problem 4. Agnes writes the following 4 statements on a blank piece of paper. At least one of these statements is true. At least 2 of these statements are true. At least 2 of these statements are false. Or at least one of these statements is false. So there's 4 statements. Each statement is either true or false. How many false statements did Agnes write on the paper? I don't know. Let's assume that there's I don't know, only one false statement. If there's only one false statement, okay, that would be this one right here would be true then. Because we said there's at least one of these statements is false, so this would be true. We're saying there's exactly one false, but at least 2 of these are false is now false. That must be false. At least one of these statements is true. Well, we do have a true one down here, so that's a true statement. And now there's 2 true statements, so that makes it true. Wait, I think we just solved it. The answer is going to be B1, B1. And you can kind of go, well, wait, that was kind of too easy. Let's make another assumption because I don't trust myself. Great, you should probably not trust yourself. What if your reasoning was terrible here and you just tricked yourself or something? So we're going to cross this out. We're going to block it in over here rather. We're going to say that there's 2 false statements now. So if there's 2 false statements, then both of these statements are true, but that means this one's true, right? This would be true because there's 2 false, then this one's true, and then at least one of these statements, they're all true then, which means none of them ended up being false. It doesn't quite fit. Something's wrong with that, right? So when you said that there's exactly 2 false statements, both of these statements become true. If I say there's 3 false statements now, let's do that. 3 false statements, then there must be 1 true. So this would be true, but this would be false. But this becomes true because there's 3 false statements. So at least 2 of these are false. Yes, because 3 of them are false. But wait a minute, how can this be true and this one also be true if there's 3 false? It doesn't fit. Does that make sense? So that's how you can go, oh, okay, I get it. That's it. Now you might feel confident It really is just B1, and you just figure it out by guess and checking like this and thinking about the implications of each one. One more time, if there's one false statement, there's only one, we have to find it, we don't know where it is, this statement is true because at least one is false. When I go here, it says at least two are false, but that's not true. Only one is false, so this becomes a false statement, therefore fulfilling it being the one false statement. Then that means at the next one up here, at least one is true. Yes, that one was already true, so this becomes true, and this becomes true because two of them are true. And that's how that works. Let's get to the next one. And now for the next one, problem number 9 in this set of rapid fire from the 2025 AMC 10A. Let f of x equal this polynomial for how many real numbers a does the graph of y equals, and think about what this is, it's a shifted graph left to right. So we're shifting this graph left to right. How many values of a would cause it to pass through the point 125? Now I initially said, well, what if x is 1 right now, and you plug it in and you get 0, and you go, well, shifting it left and right won't change anything. The zeros will still be zeros, but then it does change stuff. The 1, 0 would no longer be 1, 0, and something else would be wherever it was. You shift it left or right, would take on the value of x equals 1. So I don't know what I was thinking, but it took me a second to get my thoughts right on the problem. So now you say, okay, well, what do we do here? And then I thought, well, maybe we factor. So I went ahead and I tried factoring, and I didn't really get that far. I mean, you can do some stuff. It's not that bad. I'll show you what it looks like. You get 100x times x squared minus 3x plus 2, and that becomes x minus 2, x minus 1. And so you look at this and you're like, well, I don't know what to do with that. Maybe it'll help, though, for something else, so we'll go ahead and keep it here. Then you're like, well, how are we going to know? And so I kind of got the idea at that point. The best thing to do might be to set this. What is this? It's a y value. What is that? A y value. Maybe we could just set this equal to 25 and figure out how many times a horizontal line, basically what is your first graph? Your first graph is a cubic. If I have a horizontal line right here and it only, at y equals 25, and it only hits 1 point, then the answer would be 1, because I could shift that 1 point wherever it needed to be to hit 125, which would be somewhere on that line. But if I move it down to say here, where your tangent here and hitting there, then you're hitting 2 points, and if it crosses here, you're hitting 1, 2, 3 points. So if this was y equals 25, I would be able to shift this point, and this point with some value of a. We don't have to find it. Just any value of a would exist if I pass through 3 points. So understanding that connection between the equation and the graph, we go ahead and set this equal to 100x cubed minus 300x squared plus 200x equals 25. But I'm going to subtract 25 and set it equal to 0. That way I can just look for solutions to this. So at this point, you can divide by 25. You're going to get 4x cubed minus 12x squared plus 8x minus 1 equals 0. And from here, you might think about doing synthetic to see if you can find a root, like 1 or 1/2 or 1/4. And so you're going to make a chart, and we'll start that chart over here. So I have space. Let's say x and my y value, let's say x is 1. What do I get now? I get 12 minus 12 minus 1. I get negative 1. Let's say that I go to 0. If I plug in 0, I also get negative 1. What is that indicative of? It's kind of like a parabola. That's not a very good parabola, where when you go here, you've moved some distance away from a value, and hit something, and some distance the other way and hit the same thing, which means there's probably something that happens halfway in between here that we can check with. For example, if I plug in 1/2, which is what I did next, I get 4 times 1/8, which is 1/2. I get negative 12 times 1/4, which is negative 3. I get plus 4, and I get minus 1. This cancels. Negative 4 plus 4, and I get 1/2, which means the graph of this has crossed through the x-axis somewhere, because how are you going to get there, right? If I graph these points, this is called intermediate value theorem, by the way. If this is my y-axis, and I'm at negative 1, and then at 1, I'm at negative 1, but at 1/2, I'm up at 1/2. I'm right here. The graph has to pass through the x-axis twice, which means when the 25 was over here, it doesn't matter where the 25 is, it's still the same solution. And you must have hit the x-axis of this graph. Imagine that this is a y equals all of that. And we just want to know where y intersects the x-axis. And that's what we found. We don't know the exact points, but we found 2 of them. So the next thing you're going to do is go, okay, then what? Then we're going to go ahead and see if we can get another one. If we go to, let's see, if I go to 2, I'm going to plug in 2 and see what happens. So if I plug in 2, you're going to get 4 times 8, which is 32. Negative 12 times 4 is negative 48. 8 times 2 is 16, minus 1 again. So it looks like you're going to hit minus 1 another time, but you have to kind of have it in the proper order. 1 and 2 being negative 1 makes me think that we should check 3 over 2. So if I check 3 over 2, yeah, if I check 3 over 2, let's see what we get. 4 times 3 over 2 is 4 times 27 over 8. I'm going to get rid of this. 4 times 27 over 8 minus 12 times 9 over 4 plus 8 times 3 over 2 minus 1. So 4 over 8 is 2. I've got 27 over 2. Here you're going to have minus 27. Here you're going to have plus 12 minus 1. So it looks like we're getting quite a big negative number. Maybe not. 13.5 and 12. Very interesting of our graph to do this, though. Well, I guess it's getting more negative. Okay, yeah, so it got more negative, which makes sense. We're going to be getting more negative, so we're coming back up now. Okay, great. So actually, I went the wrong way. I probably shouldn't have done 3 over 2. If you're thinking about your graph, you were on your way down, which shouldn't surprise us. We get a greater negative number, and now as we move this way, we're on our way back up. Let's go ahead and plug in 3 at that point, which should be a lot easier to check. This is we can find the exact value if you want, but it's not really relevant. You have 13.5 and 12 is 25.5. Minus 27 is negative 1.5. It would have been negative 2.5. And what I was thinking of finding was where this point is right here. Because you're at negative 1 and negative 1 at these 2 points. At these 2. And I was thinking that by checking 3 over 2, we might find it. But it's actually going to be, I don't even know. I'm thinking about it. So it must have actually come like this. I don't want to confuse people, so I'm going to redraw this part. Okay. We don't need this for the problem solution, by the way, but I want people who are not familiar with this concept to understand. So at 0, you're at negative 1. At 1, you're at negative 1. And at 2, you're at negative 1. But at 1/2, you're at 1/2. And at 3 over 2, you're a little bit more negative. So it's actually going like this. And so now we're on our way back up that way. And we should anticipate, it's a cubic function. You're going to cross one more time. All cubic functions do that. We don't even really need to write this value. Every cubic function with a positive first term will look like this. And so we already know we're going that way, and now we're going this way. You're definitely going to hit it, and we don't need to keep plugging in numbers, which will save time. That means that since this graph has 1, 2, 3 solutions, the answer will be 3. Let's get to the final problem of this set. And the final problem in this rapid fire set for the 2025-10A, it's problem number 10. A semicircle has diameter AB, stop and take stock, kind of, got this mouse hole missing, and chord CD up here of length 16 parallel to AB. A smaller semicircle, probably this one, with diameter on AB and tangent to CD, meaning it hits at a point of tangency here, is cut from the larger semicircle as shown below. What is the area of the resulting figure shown shaded? It's not shaded on mine because I got a black marker and I want to be able to write in there, so I didn't shade it, but the whole thing is shaded except for this white part right here outside of it. So how do you start? It's like, well, we don't really know what the radius is. They didn't tell us that. You kind of look back for it, you don't see it. So I start thinking, well, maybe if I start at the center and I name the radius, like R, then maybe I could name this and this, but how would I name them? Maybe it would be better if I called their sum. And so I started thinking about if I found the center of this semicircle and I went up and I called that, like, I don't know, X, and going over here X, and going over here X. I could also have used R, little r. Then maybe I could call this part here big R minus 2x. Maybe, what would I do with that part? I don't know. But then I got an idea, because going up right here, the distance between parallel lines is constant. That's a small notebook concept, and they did say they're parallel, which means if I went up right here, it's also x. And furthermore, the point of tangency is hitting it at 90 degrees. And so same thing will happen over here. It's going to hit it at 90. But this is another small notebook concept. If you have a circle with a chord and you connect the center to that chord at 90 degrees, so if this, then you bisect the chord. In other words, you're guaranteed to hit the chord's midpoint. That would mean that this length from here over, not this one, just the one up here, would have to be 8. Oh, and then you're like, well, we do have a right triangle option now. What if I went over to here and called that capital R, and now I would have a right triangle where this is 8x and capital R. Probably would have been better with little r here, but you know, I used x on my paper and then thought about the ideal later. So now what? So at this point, you're like, oh, maybe we can make another equation over here or something, where we try to find, and keep in mind, this isn't actually drawn here, it's just what we know is there. Maybe we could do something with that, like if I went over this way, we know that's x. If I call this like A, but that's not a radius or anything, it's just a random line. Or maybe I could draw it over to here then. Don't know what that's going to do. We could drop down here and have x, but now you're cutting off a tiny piece of your don't think that's it. So then you have to go, wait a minute, what are we doing? We're finding the area. And this is a thing I tell my students all the time. It's called write what you want. Write what you want. So if you want the area, then write what that would look like in the context of what you've created. And if I do that, it would be 1/2 pi big R squared minus 1/2 pi little r, or x squared in my case. Hey, wait a minute. Won't we get something like that with x squared? And wait a minute, maybe we can just get it over there. So if I take pi over 2 outside, I'm actually looking for the big radius squared, and that's exactly what we get right here when we do Pythagorean. You're going to get 8 squared plus x squared equals r squared, and you're going to subtract x squared, and you're going to have 64 equals r squared minus x squared. So since that is exactly what we have over here, we're just going to drop the 64 in for this, divide it by 2, and we're going to get c 32 pi. Let's get on to the next batch of 5.